Dear all, I am Dr. V. Malati, Associate Professor, Department of ECE, XR University. Today's lecture I am going to take about pipelining. So, in this topic, we have subtopics, namely basic concepts, data hazards, instruction hazards, influence on instruction sets, data path, and control consideration, superscalar operation. So first let us go with basic concepts. Pipelining. So pipelining means it is the consequence of instructions going for operation. Pipelining is a technique used in modern processors to improve performance. So we should not make the processor wait for some time. So if the processor waits, automatically the performance of the system will go down. So the timing of the processor should be important. It should not be made idle. Always it should be busy by executing multiple instructions simultaneously. So, how it is made possible and effective? So, by making the processor do the instructions more at a time. So, in the same time, the processor has to perform n number of operations. So, simultaneous operation of multiple instructions. It breaks down the execution of instruction into several stages. Design of the basic pipeline. In a pipeline processor, a pipeline has two ends, the input end and the output end. So it is automatic only. So whenever we are doing any operation, we do have input stage and then output stage. So between these two ends, so automatically the extreme ends are input end and the output end. In between these two extreme ends, there are multiple stages. That means they are known as segments, such as the output of one stage is connected to the input of the next stage, and each stage performs a specific operation. So it is very simply noted as, if it is 1 and it is second, this output is connected to the second stage input, and the second stage output is connected to the third stage input. So in this way, from the input end to output end, all the intermediate stages are connected together. And then interface registers are used to hold the intermediate output between two stages. So it is one stage and it is the second stage and it is the third stage. Means what is the output taken from the first stage and what is the output taken from the second stage. Automatically they are called as intermediate output. So this output is going to next input and this output is going to next input. Suppose if it is the last stage, then the output is known as the net output. It is not going to be given to the any other input stage. So it is the final output. In the same way, it is the initial input, the first input. Remaining are the intermediate inputs. So this output is going to second stage input, means This is intermediate input. In the same way, it is intermediate input. So next one, interface registers are used to hold the intermediate output between the two stages. These interface registers are also called latch or buffer. So normally we are talking about input and output. So giving out the output data, taking in the input data. So how it will happen? It is not just magic. It has to be held by one register. So taking, holding and giving out. So for this purpose, that latches or buffers are used. So buffer or latch, they are nothing but they are the registers only. They will not do any action on the data. They just take in and give out. That is what the function performed by the latch or buffer. It won't do any modification on the data obtained from out. All the stages in the pipeline along with the interface registers are controlled by the common clock. So all are given by the central clock system. So same clock frequency will be given to all stages. Uniform clock, that means uniform clock. Execution in a pipelined processor execution sequence of instructions in a pipelined processor can be visualized using a space diagram. How it is seen. For example, consider a processor having four stages. So four stages means one instruction execution is divided into four number of stages, and let there be two instructions. So two instructions only taken in this example to understand easily, to not to make it complex to be executed. We can visualize the execution sequence through the following space-time diagram. So in the first one, without overlapping. So to save the time, we have to overlap the stages, because if you take two instructions, each instruction is having four stages. So second instruction is also having four stages. These four stages are different from one another. Therefore, if we overlap these two instruction stages, every operation will go on smoothly. They will not mix together, so that error will occur in the output. So without overlapping, suppose we are not at the stage of saving the time. Now non-overlapped execution. So normal execution. We are not taking any care to save the clock. So in this stage or cycle, stage 1, stage 2, stage 3, stage 4, because every instruction is divided into 4 stages, and then how many number of clock cycle is required. So for one clock, one stage of the instruction is performed. So second clock cycle means second stage of the instruction is executed. In the same way, for every stage operation, we need to have one clock cycle. So that is why one instruction means four stages. Every stage needs one clock. Therefore, 4 clocks. In the same way, for the second instruction, 4 stages, each performed at 1 clock means again 4 clock cycles. Finally, we need total 8 clock cycles for performing the 2 instructions, each having 4 stages. These 8 clock cycles are represented 1, 2, 3 up to 8. See, stage 1 is first clock cycle, stage 2 second, stage 3 third, stage 4 fourth clock cycle. Notice that it is I1. All 4 belong to I1, that is instruction 1. So up to 4 clock cycles, first instruction is getting completion of execution, and then fifth clock cycle, instruction 2 enters in. So the first stage of instruction 2, and in the sixth clock cycle, stage 2 of instruction 2, seventh one, stage 3, eighth one, stage 4. So time total time required is equal to 8 clock cycle. And then now our ultimate aim is to reduce the number of clock cycle. So how to reduce? Automatically, since we have 4 different stages, we can overlap the instructions. See, overlap the execution. Number 1 is stage 1, 2, 3, 4. And then in the clock cycle number 1, instruction 1 enters. So stage 1. In the clock 2, the instruction 1 enters the second stage. But at the same time, instruction 2 first stage will be executed. Since these two are different, there will not be any confusion in executing these two stages. They are entirely different. Therefore, executing these two stages at 1 clock cycle will not create any problem. In the same way, third clock cycle, the instruction 2 enters in the second stage. At the same time, in the clock cycle 4, instruction 2, third stage is performed, but for the instruction 1, second stage is performed for the instruction 1, third stage is performed, and then next one in the fifth clock cycle, stage 4 of the instruction 2 is performed, and here 4 stages of the instruction 1 is completely executed. So in the next fifth clock cycle, there is no more stages of instruction 1, because at 4 it is entirely completed execution, and in the clock cycle 5 only the fourth stage of the instruction 2 is getting executed. Next one. So normally this pipelining is adopted in RISC processor. RISC processor means reduced instruction set computer. RISC processor has 5-stage instruction pipeline to execute. So in the previous example, I told you only 4 stages for one instruction, depending on the architecture, because we are considering here it is RISC processor. and for any instruction it is divided into 5 segments so that 5 stages of instruction will be executed. So 5 stage instruction pipeline to execute all the instructions in the RISC instruction set. Following are the 5 stages of the RISC pipeline with their respective operations. So 5 stages are named as what are they? Number 1, instruction fetch. So stage 1 is instruction fetch. Stage 2 is instruction decode. Whatever is received, it has to be decoded. Now, what is decoding? What is decode? In this stage, the processor will understand the command and it understands what operation is to be performed. By saying the command, the processor understands what is to be done. That is the decode. And in the stage 3, instruction execute. So after identifying the operation, it will start executing the operation. And in the fourth stage, memory access. So memory access, what is the address of the operand? What are the data? So those will enter into this stage 4. And in stage 5, write back. Write back means after execution, definitely the processor will be having the output results. These results have to be given to some location or any output device. That is the write back. Now let us see in elaborated manner what is instruction set. In the stage, the CPU, the processor fetches the instructions from the address present in the memory location whose value is stored in the program counter. The program counter is nothing but the content of the program counter is the address of the next instruction which is to be executed. So based on that, every instruction one by one it will be executed. And in the stage 2, instruction decode. In this stage, the instruction is decoded and register file is accessed to obtain the values of registers used in the register instructions. So register file, automatically register is nothing but the storage element and it is inbuilt. It is present in the processor itself. It is not the external memory. It is internal storage for the processor. And in the stage 3, instruction execute. In this stage, some of the activities are done such as ALU operation, arithmetic logic unit operation. Arithmetic logic operations will be performed on the data which is available now. And then memory access. In this stage, memory operands. So operands means the data on which the operations to be performed. So it is nothing but the data. Operand means data are read and written from R2 to the memory that is present in the instruction. So the address of the operand will be present in the instruction itself. By seeing the address, the control will go to the particular memory location and take the data. And then in the fifth stage, in the write back stage, computed or first value is written back to the register. So the output value will be written back. Next one, performance. So in this way we are we are saving the number of clock cycles required to perform multiple instructions. So automatically we know that the processor functions very efficiently, effectively. So now we have to know about in what way the time is reduced, in what way we have saved the number of clock cycles. So it will not be random. So how it is calculated, how it is being known. Let us see. Performance of a pipeline processor. Consider K segment pipeline. So number of stages will be equal to K. Let us assume that the clock cycle time as TP. So processor time is TP. Each clock is having the time of TP. Let there be n tasks. So n number of instructions to be completed in the pipeline processor. So each task is divided into k number of segment. Now the first instruction is going to take k cycles to come out of the pipeline. So first one is k segment, means k number of clock cycle is required for that instruction from the beginning to end. From the beginning to end. But the other is n minus 1 because we are overlapping the instruction. Once the first instruction comes to the second stage, the second instruction comes to the first stage. So, if it is ends in n number of clock cycles, the second instruction automatically will end in n plus 1. N plus 1. One more addition it needs. So, it will take one clock cycle, total of n minus 1 clock cycle. And then, the time taken to execute n instruction in a pipeline processor, the formula is ET pipeline is equal to K plus, so K number of stages plus n minus 1 cycles. It is equal to K plus 1 minus 1 into TP is nothing but the number of clock cycle is nothing but the TP only. That is why K plus 1, K plus n minus 1 into TP. In the same case, for non-pipelined processor, the execution. So we do not have any overlapping. So continuously each and every instruction is taking the, suppose K segment means every instruction K clock cycles it needs. K cycles it needs. For one segment, one clock cycle. For K segment, K number of clock cycle. If n number of clock cycle into n number of instruction into K number of division for one clock cycle TP. So all are multiplied. So without pipelining, I mean non-pipelining means n into K into TP. Next one, so speed up. So speed up now, it is the very important factor. Speed up means saving the speed. Saving the clock cycle means automatically, saving the clock cycle means we are automatically increasing the speed. It is going to be fast. The operation is to be fast. Even that is what the meaning. So saving the clock cycle is not only the matter. We are increasing the speed of the processor. So in which way, how far the speed is increased? So how many number of clock cycles is saved, we can calculate. Now how many times the speed of the processor is increased? Either 2 times or 3 times. That is the speed up of the pipeline processor over the non-pipelined processor. So when comparing two, it is equal, how it is calculated. When n number of tasks are executed on the same processor is. So same processor means we are going to calculate when it is non-pipelined, what is the speed. When it is pipeline, what is the speed? Both are taken as the ratio 1:2 like that. So the pipeline is to non-pipeline. What is the value? We are going to calculate. So S is equal to, the formula is given, performance of non-pipelined processor divided by, so is to only, divided by performance of the pipelined processor. As the performance of the processor is inversely proportional to the execution time. So performance, if speed increases, time decreases. If time increases, speed will decrease. So that is why they are inversely proportional. We have S is equal to ET non-pipeline divided by ET pipeline. So we know already that without pipeline, we know the formula N into K into TP. With the pipeline, K plus N minus 1 into TP. So if we reduce, if we simplify this equation, we do have n plus k divided by k plus n minus 1, because this TP, numerator and denominator, they will get cancelled. Finally, we get the formula S is equal to n plus k divided by k plus n minus 1. So next one, when the number of tasks n is significantly larger than k. So what is the meaning? If one instruction is divided into 4 segments, but the number of instruction is 8. Division is 4, but the number of instruction is 8 or 7 or 9. Anyway, number of instruction is more than the number of division. That is what the meaning. Then n is far greater than k. So this is the condition now we are assuming. S is equal to n into k divided by n, because that n minus 1 plus k we have seen in the previous formula. No? So it will be reduced to n only, because n is far greater than k. So it when compared to the n value, this k value is very negligible. That is why n into k divided by n. So this n cancelled. S is equal to k, where k is the number of stages in the pipeline. So how many stages? If it is 4, then speed up factor is equal to 4. That is what the meaning. S is equal to K. S is equal to speed up factor is equal to number of segments in the instruction. Also, efficiency is equal to given speed up divided by maximum speed up. So given speed up is equal to S, what we have calculated, divided by maximum speed up. We know that maximum speed up, we know that S max is equal to 4. We have already seen maximum speed, which is equal to number of segments in the instruction. So 4 means for beyond 4, the speed will not be increased. 5 times speed up we will not get. Only it will be equal to the number of segments, the number of stages in the instruction. That is why beyond that we cannot get. That is why here S max is equal to K they have given. It is ultimate. So efficiency is equal to S by S is normal speed up divided by K. S by S max is equal to it can be also written as S by K. Now throughput. So finally throughput, efficiency throughput is equal to number of throughput is nothing but the performance of the processor. Number of instructions divided by total time to complete the instructions all together. So number of instructions to complete to get completed, how much time it is taking into account. It is equal to number of instruction n divided by k plus n minus 1 into Tp, which we have already seen with the pipeline k plus n minus 1 into Tp. That is the total number of complete instruction, because we have already reduced the time taken to. Next one, the cycles per instruction. So CPI is equal to cycles per instruction. This value of an ideal pipeline processor is equal to 1. So ideal value is equal to 1. CPI should be equal to 1. Performance of pipeline is measured using two main metrics as throughput and latency. So latency means automatically late latency. But we should not make the processor delayed. So that delay should be reduced. And then throughput. So throughput is nothing but the performance. And performance and so late delay means it is time increase. Reduction in time for performing the instruction without any delay all the time. Here time means clock cycles we provide. All should be utilized efficiently without any wastage of clock cycle. That is what the latency. Now throughput, it's a measure of number of instruction completed per unit time. Number of instruction completed per unit time is the throughput. It represents overall processing speed of pipeline. Overall processing speed of pipeline. And then higher throughput indicates processing speed of pipeline. Higher the throughput, higher the processing speed, and calculated as throughput is equal to number of instruction executed per execution time. So 1 unit time, how many number of instructions are executed, that is equal to throughput. It can be affected by pipeline length. So how many instructions are given as pipeline? If more, then the throughput will automatically become reduced. And then clock frequency, if more clock frequency, no problem. Less clock frequency, automatically speed will become reduced. And then efficiency of instruction execution and presence of pipeline hazards. So any errors present in the, any problem present in the pipelining. And then stalls. Stalls means staying, delaying, and it is not continuously moving on, it is stopping at any time, at any place. This is stalls. So these are all the factors that are going to affect the pipeline throughput or latency. And then, so we see about the latency. It measures time taken for single instruction to complete its execution. So execution time, it's a measure of time required for executing the instruction. It represents delay or time it takes for an instruction to pass through the pipeline stages. So pipeline means it is not having only one stage. It is having several stages. So all through the stages, the instruction has to be executed. That is why it represents delay or time whenever it starts from the first stage to last stage. What is the delay? So in between two stages, there should not be any time delay. If delay or unit time occurs, then it is equivalent to delay and delay or latency, and it will automatically affect the efficiency of the processor. So in between, how to say simply, in between two stages there should not be any delay, and it is calculated as latency. It is equal to execution time divided by number of instruction executed. It is a formula. So total time divided by number of instruction. It is influenced by pipeline length. So the length of the pipeline. So automatically length of the pipeline means it is equal to the number of instruction present. And then depth, clock cycle time, so frequency, instruction dependency. One instruction output, it is dependent on the another instruction input. Suppose two instruction, the first instruction output is given to the input for the second instruction, then it will create a problem, because before getting that instruction data, the first instruction compulsorily has to be completed. Then only the output given as input for the second instruction will be solely correct. Otherwise, if the execution is partial for the first instruction, then the input given to the second instruction will not be correct. That is why the dependency should be taken care of carefully. Otherwise, the problem, I mean execution will become wrong. That is instruction dependencies and pipeline hazards. It is an internal problem. Advantage of pipeline. Increased throughput. Okay, so throughput, to increase the throughput only we are doing the pipelining. It will enhance the throughput capacity of CPU and enables the number of instructions to be processed at the same time simultaneously at different stages, because same stages to instruction will not come. It will lead to the improvement for the instructions accomplished in the given period of time, thus improving the efficiency of the processor. Next one, improved CPU utilization. So CPU timing, CPU utilization means CPU will never become idle. At all time it will be used for the function operation. From superimposing of instructions, I mean superimposing is overlapping. Pipelining helps to ensure that different sections of CPU are useful. So different sections, components, blocks of the CPU are useful. This gives no time for idling of the various segments of the pipeline and optimally utilizes hardware resources. So, not only CPU idle, but also CPU should not be idle. That is the case, okay. Not only CPU, whatever the hardware resources available in the CPU, they should not also become never idle. They should not become idle. Always it should be utilized under operation. Okay. Then higher instruction throughput. Pipelining Pipelining occurring because when one particular instruction is in the execution stage, it is possible for other instructions to be at varying stages of that already we have seen in the diagram. First stage, first instruction only fetch stage it will enter, and second stage when it enters decode, the second instruction will come into the fetch stage. That is what mentioned here. So two instructions will not come into the same stage, different stage. Then only the confusion will not occur. It will go on smoothly. Execute at memory access and write back. These are the 5 stages in RISC processor as we have already seen. And in this manner, there is concurrent processing going on, and the CPU is able to process more number of instructions in a given time frame than in non-pipeline processor. So again and again the same reason, same time, different stage, multiple instruction. There will not be any confusion or erratic output. Better performance for the repeated task. Pipelining is particularly effective when all the tasks are accompanied by repetitive instructions, so looping operation. So, same instruction multiple times means it will be very useful. Super good performance is provided by the pipelining. That is what repetitive instruction. It is repeated operation. Then we can expect more, even more performance, because the use of the pipeline shortens the amount of time required for each instruction to get completed. And then scalability. Pipelining is RSVP implemented in different types of processors. Hence, it is scalable from simple CPUs to an advanced multi-core processor. So, it is scalable. The scalability is improved. And then disadvantage of the pipelining, pipeline hazards. Pipelining may result to data hazard. So incorrect data. So in the previous slide I told you, if a second instruction depends on the first instruction output, automatically data hazard will occur when the first instruction is not completed its execution, because it has to supply the input to the second instruction. That is the name given to it, data hazard, whereby instruction depends on other instructions. Control hazards which arise due to branch instruction. So control means automatically if jump instruction, if or else condition occurs, if the condition is not satisfied, it will branch to other location. If the condition is satisfied, then it will continue the sequence of the steps. Next one, arise due to the branch and structural hazards, whereby there are inadequate hardware facilities. So, whatever the necessary hardware resources, they should be completely available. If it is not available in correct time, automatically structural hazards may occur. Some of these hazards may lead to delays, hence have strategies to manage them to ensure progress is made. And then increased complexity. So if we do not understand the entire operation, then automatically complexity will occur. And pipelining enhances the complexity of the processor design as well as its application as compared to non-structured, non-pipelined system. Because non-pipelined means one instruction getting completed, after that only second instruction enters into, and after completion third enters. Time will be more, but there is no hazards. One after the other means giving input, taking output, giving input, taking out. That's all. In between, there is no complexity. There is no dependency. And then pipelining stages management dealing with the risk of the instruction sequence contribute to the design and control considerations. Then stall cycles. So this is also one disadvantage. When risks are present, pipeline stalls. Stall means already I told delay in the processor at one stage. If it is stuck, then it will not do anything at that time. That is stall. Or bubbles can be brought about, and this procedure idle time in certain stages in the pipeline. So ideal stage only, ideal, the time is wasted, that's all. These stalls can actually remove some of the cycles occurred by pipelining, thus reducing the latter's efficiency. So stalling means it will automatically remove some, it will waste the sum of cycles. So if it is delaying at one place, if it is stalling, if it is not doing anything and staying in one place means during that time, how long it is staying, then how that depending on the time duration, number of clock cycles will be wasted because clock cycles are continuously moving on. Suppose if it is not doing anything, how long it is staying, that many number of clock cycles are wasted. Next, every instruction must still go through all the pipeline stages, and the time it takes for a single instruction to execute can neither reduce nor decrease significantly due to overhead. And then hardware overhead. It increases the complexity in designing the pipeline due to the presence of pipelining registers, because in between in all intermediate stages we have to provide the latch or buffer, which are otherwise called as storage devices or registers, and so every stages we need, and the control logic used in managing the pipe stages and the data. This not only increases the cost of the bus, but also forces the integration of more complicated and thus costly hardware. So integration of the all components one by one consequently in correct manner will create some complexity as well as cost, expensive also. So now, what is a hazard? So we have seen so many hazards, namely data hazard, control hazard, structural hazard. First, let us see what is the data hazard. Data hazard occurs when the instruction that exhibit data dependency. So the second instruction input depends on the first instruction output. Output input nothing but data only. That is data dependency. Modified data in different stages of a pipeline. So hazard causes delays in the pipeline. There are mainly three types of data hazards. Number one, raw, read after write. This is flow or true data dependency, another name given to it. And then WAR, write after read, anti-data dependency. And third one, write after write, output data dependency. So next one, so everything is given in detail. Let there be two instructions, namely I and J, such that J follows I. Then instruction depend on result of prior instructions still in the pipeline. So dependence of depending on the output from the previous instruction. It can occur among the operands. So operand means data only. Data on which the operation is to be performed in the instruction at the pipeline stages. And then it occurs when instructions read or write registers that are used by the other instructions. So read or write means taking the output from the previous instruction. That is write operation only. And then so first one, read after write hazard occurs when the instruction J tries to read data before instruction I writes it. So I does not complete the execution. If it completes, it will give the data to J. But J is fast. That is why before execution it is trying to take the data from I. Then what will happen? The data will be incorrect. So that is stated in terms of statement I R2. It is minus 2 plus R3. It is less than or equal to. I mean less than minus R1 plus R2. J is R4. It's actually arrow mark. R2 plus R3. This R2, from where it comes, R3 is common data only. It is supplied with R3 data. It is also supplied with R3 data. No problem. But R2, where from it comes? It is coming from the output of the I instruction. So once if it completes R1 plus R3, then only the R2 value which is taken up by J instruction will be correct. WR. Next one, right after read hazard occurs when the instruction J tries to write data. Here read data, here write data before instruction I reads it. Here I writes it. See the instruction R2 belongs to R1 plus R3. But J R3 belongs to R4 plus R3. So here what is R3? R3 here R3 is common data. Here R3 is common data. But here R3 is equal to R4 plus R5. So R3 value is written, I mean it is edited by the addition of R4 plus R5. But this R3 is previously what before calculation what is the value of R3. But since if it is late, then whatever the R3 will be equal to R4 plus R5. But this R3 is different, this R3 is different. That is why they tries to write data. They tries to write data here before instruction I reads. Suppose if I is delayed, then this R3 is equal to this value. But in the instruction, it is not the meaning. Suppose if R3 is equal to 2, that 2 is coming here. And then R3 it is equal to R4 plus R5 means suppose 2 plus 3 it is 5. So this R3 2 is different, R3 is equal to 5 different. That is why before replacing R3 with the 5, this 2 value should enter here. That is what the meaning. And then W after W. Right after right hazard occurs, the instruction J tries to write output before instruction JI writes it. See here, instruction I, what it says, R2 is replaced by R1 plus R3. But the instruction does R2 is equal to R4 plus R5. So our first I instruction is performed. So we are getting one value. Second J instruction is performed. We are getting another value for R2. Suppose R2 is performed first, then whatever the R2 value will be different, and what you are reading in the I instruction R2 will be different. But first you need to have the R2 value of equal to R1 plus R3 only, not R4 plus R5. First R1 plus R2. Second only R4 plus R5. If there is any timing difference between the two, whatever the output you are getting from J will not be correct. First you should get the first I value, I instruction output only you should take. That is what the meaning. So before I, J tries to write the output in R2, then it is known as write after write hazard. And then the same thing how it is given diagrammatically. See here, same thing. I instruction 1, instruction fetch, instruction decode, instruction execute, write, uh, uh, write back only RW, store the result write. Okay, and next one, I2. So in the second clock cycle, it starts IF, ID, IE, RW. And then I3, IF. So here it will be left. It will be, no, there is no instruction execution. It will be left. Because if it starts here, then automatically two stages of two instructions will be equal, same, then it is also erratic. That is why after leaving two clock cycles, the third instruction will start. In the same way, fourth instruction after leaving three. And fifth instruction after leaving four clock cycles, it will start. Now, here, see, suppose this yellow mark. Why yellow mark? This yellow mark is memory access required. So, it has to take the data from memory. So, it has to reach to the address of the memory and taking the data, it will take time. In the same way, red is may or may not be may be required or may not be required. Memory access, I mean the data from the memory will be required or not required. So here after T4 and T5 resource clash likely. So that is why I have given this straight line or T4. In this T4 clash will occur. Clash will occur. In the same way, T5 clash will occur. Why clash will occur? Because of the data hazard, because of the hazard, instruction hazard. We are seeing here instruction hazard. So, in this way, the instruction hazard, data hazard means data only, the error will occur only in the data. But in the instruction hazard, clashing of the two stages of different instruction will occur. That is the instruction hazard. So data means within the data only, data from one instruction to another instruction. But hazard within the instruction means it is very serious condition. Instruction hazards in pipeline are situation that disrupt the normal flow of instruction. So everything will become wrong. These hazards can be categorized into three main types: structural, data, and control. So all hazards are already we told. Control means it is due to the branching of the control. Branching. So the entire sequence of the program will be disturbed. Due to that, any problem occurs, that will be known as control hazard. And dependency of the data from one input to output, then it is data hazard. Within the instruction, if clashes occur, so we assume that memory access required. We assume that memory access may or may not because of the data. So to fetch the data from memory, it will take time. It will take time means clock cycle will be wasted. Clock cycle will be wasted means so it will not, it should be like this only. RW, IE means IE only. Suppose if late RW comes, then it is wrong. In the same way here, decode only. Instead of decode, if instruction fetch comes or instruction execution comes, then automatically instruction stage is wrong. Stage is wrong means instruction wrong. That is the instruction absorbed. So dear all, with this I conclude this presentation. We will continue in the next video.